This time we are going to talk about angular momentum. So momentum, in fact, it's a need in physics. For example, general students think that if an object can move only if a force acts on an object. And if the force is removed, everybody thinks that object must stop. But the object does not stop if the force is removed. Object continues moving. So why? Why this object continues to move? Assume that you hold a rock in your hand, and then you push this rock with your hand. Because you are pushing you are using your muscles, and with these muscles you are able to push the object, move the object. But as soon as you release the object does not stop. Object continues moving. Question is this: why? Why object continues to move even if you stop the contact? So this is the question, and then many years scientists couldn't get the answer. At the end, they developed a quantity which is known as momentum. Momentum is explaining that. Why object continues moving even if the force is removed. We say that this force, when you push an object with your hand, or when you apply a force on an object, you give object some momentum. So object gains momentum by this force. And as long as this momentum is kept by the object, is conserved by the object continues moving. It's a need to explain the motion of an object after a force is removed. Maybe you remember last year you studied an equation like this. F times delta t is equal to delta p. Anybody remember this equation? F times delta t is equal to delta p.
You mean the
Impulse, yes, impulse. F delta t. In fact, this equation is telling you if a force acts on object by some time, this object gains linear momentum. Object gains. Yani, if you want object to gain momentum, you should apply some force by some time interval. If you apply a greater force, momentum change becomes greater. If you apply a force in a longer time, momentum change becomes greater. Yes, momentum change, yani that momentum object gains depends on three things. One of them is force. Second one is time interval which this force is applied. So one thing is this: why object moves after you remove the force? Because object gains the momentum. Second thing, momentum depends on what? So I will start by linear momentum. Object's linear momentum, last year you studied, depends on two things. One of them is the object's mass. Second one is object's velocity. So mass and velocity, why they are so important? Assume that there are two vehicles. One of them is the truck, very large, huge mass truck. Second one is an automobile. So both are moving with the same velocity, same speed. So if I ask a question, which one is hard to stop, most probably your answer will be the truck, because mass of the truck is greater. Momentum also defines that how difficult to stop an object's motion. For example, truck has a greater momentum than automobile because truck is a greater mass. So if an object has a greater mass, so it is a greater momentum. That's why it's hard to stop the truck harder to stop the truck than the automobile. So second one is, assume that there are two identical automobiles, identical. One of them is moving faster, the other one is moving slower. Which one is harder to stop? Of course, the one with a greater speed is harder to stop. So that's why it has a greater momentum. Momentum, in fact, saying you that, yes, if an object has a greater momentum, so it is harder to stop this object's motion. So this is in translational motion. And momentum depends on, in translational motion, two things. One of them is the object's mass. Second one is object's velocity. But we don't talk generally about the velocity in this 12th grade. Object's linear speed. And you can calculate, in fact, the momentum by m times v. Momentum. It's a vector quantity. It was like a vector quantity. Mass is a scalar quantity multiplied by velocity. This is the equation for calculating the linear momentum, which is about the translational motion. But same question can be asked in rotational motion as well. So if you start rotation of an object, for example, Earth is rotating. Why? Why still moving? Why not stops the rotation Earth? Initially, some angular momentum is given this object. Yani, in rotational motion, we have angular momentum. In translational motion, we have linear momentum. So both have momentum. So Earth is rotating, still rotating, because Earth gains some angular momentum. As long as Earth keeps this angular momentum, it will continue rotating. So then angular momentum also very similar to the linear momentum. If an object is rotating with some angular speed, in linear momentum, linear speed we have. And in angular momentum, of course, we are going to have angular speed. If an object is rotating with some angular speed, this object possesses gains, or it has some angular momentum. This angular momentum is represented by capital L and determined by two things. One of them is object's moment of inertia I. Second one is object's angular speed omega. It is very similar. So remember, in translational motion, we have mass. In rotational motion, we have moment of inertia. In translational motion, we have linear speed or linear velocity. In rotational motion, we have angular speed, angular velocity. These two quantities are very similar. Just only difference is one of them is about translational motion. Second one is about rotational motion. Even equations are really similar to each other. So then equations. First equation is about translational motion. In translational motion, you studied last year this one. So P, which is the linear momentum, is equal to mass of the object multiplied by velocity of the object or speed of the object. But angular momentum, so L, I times omega. I is moment of inertia, omega is the angular speed. So L becomes, in this case, I times omega. Again, if you multiply moment of inertia of an object with its angular speed, you can calculate the angular momentum of the object. So this makes sense because if assume that there are two disks, one of them is a greater moment of inertia, the other one is a smaller moment of inertia. Both are spinning with the same angular speed. Which one is harder to stop? The one with a greater moment of inertia or the one with a smaller moment of inertia? What do you think?
The one with the greater.
Of course, it's harder to stop because moment of inertia is resistance of object to accelerate. When you try to stop an object, you try to accelerate it. That's why object resists that. Greater moment of inertia, it's harder to stop. Second one is identical disks. One of them is spinning with a greater angular speed than the other one, smaller angular speed. Of course, the one with a greater angular speed is harder to stop. That's why it has a greater angular momentum. So angular momentum, as I said, is very easily calculated, very similarly calculated. These two quantities are very similar. One of them is m, the other one is moment of inertia. Second, in the first one we have linear speed, in the second one we have angular speed. P is the linear momentum, L is angular momentum. So linear momentum's unit, last year you calculated very easily. Linear momentum as a unit, because mass is kilogram, speed is meter per second, so kilogram times meter per second. Same thing can be done in angular momentum. So angular momentum will have a unit which is moment of inertia, kilogram times meter squared. We know about that. Angular speed is radian per second. However, remember, we added this radian as a unit. It is normally radian has no dimension. So that's why we are generally writing omega in the equations by 1/seconds. So that's why you are going to multiply kilogram times meter squared by 1/second. When you combine them, you will get kilogram meter squared per second is the unit of angular momentum. Kilogram times meter squared per second. Also, this is a ministry exam question. They asked what is the unit of angular momentum, which is kilogram times meter squared per second. Yes, this is the 2017 second term ministry exam question. A merry-go-round has a mass of 525 kilograms. So mass is given. Let's write it. 525 kilogram, which is the mass of merry-go-round, and radius of this merry-go-round is 2. Merry-go-round is a disc. disc-shaped object which is spinning with some angular speed, and you are standing on, general children are standing on it and then turning together with the merry-go-round. I mean, fun, they're having fun with this device. It's 2 meters, reduces as you see very big, 2 meters. And if this disc, merry-go-round, as I said, it's a disc. If it rotates with an angular speed of 0.2 radian per second, so omega is given, which is equal to 0.2 radian per second. What is angular momentum? Calculate the angular momentum of this merry-go-round. We know angular momentum is calculated by I times omega. So omega is given, but I is not. In this moment of inertia for the disk is 1 over 2 mr squared. We'll learn about this one, this table. And also this is given in the exam. By the time they are generally giving moment of inertia equations in the exam. So I is for a disk 1 over 2 mr squared, 1 over 2. M is 525. Radius of the disk is 2 meters, 2, but squared, don't forget squared. Sometimes students are forgetting this square. Be careful about this. 1 over 2, I is equal to 1 over 2 mr squared. So then you can calculate I. Let's calculate it how much. 525 multiplied by square root of 2 is 4 divided by 2, which is equal to 1050. So moment of inertia of this merry-go-round, it's a disk, is equal to 1050 kilogram meter squared. Now we are ready for calculating the angular momentum. Moment of inertia is 1050. Angular speed in the problem is given as 0.2, so 0.2 radian per second. When we multiply them all, we will get the 110 kilogram meter squared per second. This is the problem asked in 2017. This problem, in fact, a part of the sample problem. In this title in the book, we are not calculating angular momentum alone. Just there's a sample problem which is about conservation of angular momentum. Next title we will study tomorrow. They part a part of this problem and then asked calculating angular momentum. So that's why this problem is a part of the sample problem, but not complete sample problem. Sample problem, it's a part of sample problem as well. Normally, as I said, sample problem is just about the angular momentum. But before starting that title, I again divided this sample problem into 2 parts. How to calculate the angular momentum. Question is this like this. A 65 kilogram student is spinning on a merry-go-round that has a mass of 525 kilogram and radius of 2 meters. As I said, it's a disc-shaped object and its radius is given as 2 meters and mass of this merry-go-round is 525 kilograms. If student, that 65 kilogram student, is standing at the edge of the merry-go-round, which is spinning with 0.2 radian per second, calculate angular momentum of A, merry-go-round alone, B, student alone, C, the total angular momentum of the system, yani student and merry-go-round together. So first one, in fact, we calculated in the first problem, but the question says that there is a student. This student is standing at the edge with a mass of 65 kilograms. Yeah, this system has 2 components. One component is the student, second one is the merry-go-round itself. So calculate the merry-go-round alone. I already did this in the previous one. So this one was about calculating the angular momentum of merry-go-round, and we calculated it by 2,210. That's why I will skip this part, check previous one, 210 kilogram meter squared per second. Student alone, now this part is important, student alone. So as this merry-go-round is spinning, of course, with an angular speed of 0.2 radian per second, so both merry-go-round students will have the same angular speed. Yani student will have this angular speed of 0.2 radian per second, and merry-go-round will have an angular speed of 0.2 radian per second. Both will have the same angular speed. But now follow the student's path. Student's body is following a circular path. Is it correct or not? As merry-go-round is spinning.
Yeah.
So then you are going to treat the student as a
Point
mass. Yes, point mass. Now go to the table. Go to that table. We started at the beginning in this table. So point mass about an axis is, what is moment of inertia equation for this? mr squared. So moment of inertia of the student will be mr squared in here, because student is following a circular path. So that's why you should write moment of inertia of as 0.5, mr squared. Let's write it. So student's moment of inertia will be, because it's following a circular path, then keep in your mind, if an object follows a circular path, its moment of inertia will be mr squared. In this section, you are going to meet these types of questions a few times. So student moment of inertia about an axis I is equal to, now let's calculate it. I student is equal to mass of the student multiplied by radius of the circular path of the student. So mass of the student is 65. R is 2, but square of 2. So we can calculate the moment of inertia as 65 multiplied by 2 squared is 4, which is equal to 260. 260 kilogram meter squared is the moment of inertia of the student on this circular path. Then calculate the angular momentum of student. Moment of inertia of student multiplied by angular speed of the student. So moment of inertia is 260. Angular speed is common for both student and the merry-go-round, which is 0.2. Multiply them. 260 multiplied by 0.2, which is equal to 52. 52 kilogram times meter squared per second is the angular momentum of student. What about merry-go-round? We calculated in the first problem. Merry-go-round is an angular momentum of 210 kilogram meter squared per second. Angular momentum of the system. Yani you are going to add them. So L for system total is L for merry-go-round plus, so I wrote in here, right? L times merry-go-round plus L of student. Merry-go-round is 210, student is 52, add them, which is 262 kilogram meter squared per second. This is the total angular momentum of the system.